Hello, everyone. I'm Sagar Sumit. I'm a database engineer at OneHouse. And today I'm going to talk about transformative Lakehouse technology, Apache Hudi, and how it can help you build an intelligent Lakehouse platform. A little bit background about myself. So I am a database engineer at OneHouse, where I mostly work on the transactional engine of Apache Hudi, which we'll look into detail very shortly. I'm also a committer at Apache Hudi. And prior to that, I was a senior engineer at AWS Relational Data Service, working on Amazon Aurora, specifically on the control plane of Amazon Aurora. And before that, I was a senior software engineer at Grab, building their payments data platform. And I started my career at Oracle doing heterogeneous replication, CDC, using Golden Gate. So what are we going to learn today? So today I want to talk about a little bit about origins and history of how Hudi came into being and how it evolved. Then we are going to dive deep into the Hudi stack, learn about different components that make up the Hudi stack. And I'll very briefly mention the Hudi community and what we have in our roadmap and open the floor for any questions. So from a timeline perspective, Hudi originated at Uber in 2016. But what was the motivation behind it, right? So Uber had, at that point of time, 120 terabytes of raw trips data being ingested every 8 hours. And there was also a movement from warehouse to lake. And these trips data were also being updated. So actual change out for that 120 terabyte bulk ingest was actually 500 GB. That's half TB for every 120 TB of bulk ingest. But um, in order to do that, you had to fully recompute every 6 to 8 hours, right? So the ingest performance was very poor, and there was zero concurrency control. So we needed something. What were the missing pieces that this kind of workload pattern brought up? First, we needed something to be able to upsert that supports not only inserts but also updates. And then, given the importance of GDPR, we needed something that could efficiently delete as well. Um, as you may have seen that while you're ingestion, it's very hard to to run a delete job without really blocking the ingestion. The third missing piece was the incremental ingestion part. That is, you just figure out what has changed between time t minus 1 and time t and apply those updates, much like the database systems. You have write ahead log and you just apply those updates on the database. Here, we wanted to do something similar. In a nutshell, what we wanted to build was a transactional data lake, which is also popularly known as Lakehouse. So Hudi started as a serverless transactional layer on top of lakes, building these databasey features directly on top of lakes, right? So you have this cloud storage as the base layer, and you have your Parquet files or data files in some format on top of cloud storage. Hudi metadata and transaction logs, which is nothing but the event timeline. We'll look into that later. Together with Hudi table APIs for writers and readers to ingest and query the data, right? The interesting thing about the model, as we'll look into it later, Hudi provides two kinds of table types: copy on write and merge on read. Each of these table types have their own benefits, and there are certain trade-offs. And different query types as well. Snapshot query, which gives you the latest snapshot of the table, read optimized query, and then incremental query times, eventually using which you can do time travel. So let's dive into what Hudi Data Lake looks like. First, it is kind of, as I mentioned before, a database abstraction for cloud storage, and it's for near real-time ingestion use cases. Well, you already have batch ingestion, right? And then you have streaming technologies such as Kafka, which provide ingestion for event data being produced every few seconds. But this gap, right, where you want to ingest between order of few minutes to an hour, let's say, that's what we call near real-time ingestion. And there was nothing really helping with near real-time ingestion. Essentially, you had to do the batch ingestion. There was no other choice, right? So Hudi brought this incremental ETL with asset guarantees, as we'll look into it. So how has Hudi evolved? Well, it started at Uber and was open sourced by Uber. Um, it was picked up by adopters and other companies. And we added support not just for Spark, but Flink Engine in 2018. It was incubated in Apache in 2019. By the end of 2019, AWS also had official support in EMR for Hudi. In 2020, it graduated as top-level project of Apache. And since then, we have seen rapid adoption on across various domains at companies working at different scale on different cloud with different cloud service providers. In 2021, post-pandemic, OneHouse was founded. OneHouse is a company which provides this whole streaming, which provides this whole Lakehouse platform using the underlying technology Hudi. And 2020, we are already halfway past 2022. We see a very strong momentum, and we are working towards 1.0 version. We'll look into the roadmap, what unique features we have got for version 1.0. So today in the industry, Hudi is being used by companies at different scale, from few hundred terabytes to exabyte scale. These are just some links for your reference, which you can look at how companies are deploying Hudi for different use cases. So let's dive into Hudi. Oops, I just missed one slide. So this talks about the community, which, as you can see, there has been a phenomenal growth in adoption of Hudi since the pandemic. And there are more than 2,000 Slack members, more than 300 contributors, more than 20 committers. We have seen 400% year-on-year growth on Hudi's bundle downloads. Let's get into the concepts of Hudi. As I mentioned before, there are two table types in Hudi: copy on write table and merge on read table. So what does copy on write table looks like? It's essentially, you ingest, you write some data, you have raw Parquet, you have Parquet files, and the second batch of ingest is gonna copy over that data and produce another file group. So I'm talking about file group here. That's an important concept in Hudi. Why don't we just talk in terms of files? Why not we just talk in terms of files? Why talk in terms of file groups? Well, file groups are essentially a collection of one base file and latest versions of those files, which we call file slices, right? Together they make one file group. So in copy on write, you'll see that that Hudi creates essentially a copy of the previous file group. Here the trade-off is that you get your write amplification is higher, but on the query side, you don't have to do any merging. The latest file version, right, that's contain your snapshot of the table, and you don't have to do any merging while reading the table. Another table type is merge on read, where you write the base file once, and any record getting updated first get logged into these log files, log files, which are here in orange colors. And we have different versions of these log files as well. So both A prime, A double prime are log files for the base file A. which was produced at time t0. And together, ultimately, when compaction kicks in, they will merge these and produce a new snapshot, which will basically be merging A and A prime to produce this A double prime and B, right? So what's the trade-off involved here? Well, the writes are very fast. The updates are logged into a new version. It doesn't have to look up which file group to go ahead and rewrite again. There is very less write amplification. And well, on the query side, then you need to perform this merging, right? For snapshot query. Hudi also supports merge on read table, supports read optimized query, as you can see here in the end. And the read optimized query basically reads the base files. Those will be super fast, just like reading your raw Parquet files or copy on write tables. But if you, in most cases, you want to do snapshot query, and in that case, merge on read table incurs some merge cost, which is within reasonable bounds. We'll look into that, how we index the data to help us look up which particular records fall, what's the latest log file for this particular record key, right? So reading and writing Hudi tables involves this mechanism. Let's look at this example, right? So what we see here, let's go back. So you have an absurd operation with inserts and updates coming at 10:10. You had a version written at 10:05. Now, this data gets committed. There was another version written at 10:05, and this data goes ahead and it's committed at 10:10 in this particular file ID 2. Data committed at 10:10, right? So the records coming here were pertaining to file ID 2, and they got committed at 10:10. What happens here is that a new file slice is produced. When you're doing read optimized query at 10:10, you're basically reading these base files. That's it. You are reading base files for each of the file groups. You're not reading the log files. But when you do snapshot query, while reading, the base files and the log files are merged together to give you the latest snapshot. And essentially, what you'll get is also the updates that were done at 10:10. This is, please note here, this is not to say that you won't be able to see updates ever, right? Let's say a compaction kicked in between, and Hudi has a mechanism to asynchronously compact the data. In that case, the merging would have happened already, and both your read merging would have produced a new version of base file, and both your read optimized query and snapshot query would give you the same result. An incremental query is essentially what it suggests. Hudi requires you to specify these start and end timestamps, and Hudi will give you what changed between those two results, right? So Hudi ecosystem, it's totally query engine agnostic. You can use interactive query engines like Presto and Trino to query the data. You can even use Spark or traditional warehouse like Amazon Redshift to query the data. Hudi supports ingestion through multiple data sources, from relational database to event streams coming from Kafka. And your base lake storage layer consists of not just HDFS, but compatible with all cloud storages as well. Let's look at the Hudi stack. That's where we're going to spend most of the time here. So is Hudi just another table format? That's one of the most common questions that I guessed. Well, as you can perceive from the evolution of Hudi, that it was not designed as a general purpose format, right? The problem statement that we started with was totally different. It was not about organizing the metadata of the table. It was about solving a problem, solving use cases, near real-time use cases, right? Hudi is intended to play nice with the high format. It is the way it evolved over time, we built our own native table format, which was more helpful for incremental ingestion. So if you just want to do bulk insert, go ahead, do bulk insert. Hudi supports that. But the real value of Hudi comes with this incremental ingestion. When you have, let's say, a certain fraction of data being updated in each batch, then you'd see the indexing features of Hudi helps it amortize the cost. And after a certain number of rounds of ingestion, Hudi will show log growth in log scale, ingestion latency, and Hudi will actually stabilize after a few rounds, but other formats will keep growing linearly. So what is Hudi? If it's not a table format, is it just a transactional layer on data lakes? Well, yeah, kind of. Hudi does provide transactions, updates, and deletes. And the basic architecture, it's driven by event logs. So Hudi has a timeline of events, which serves as a serialized order of whatever happened to the table. But Hudi, more than just a transactional layer, it's a serverless database. Not just that it supports efficient updates and change capture, but it supports different types of indexing mechanism and the ability to index without really blocking your writes. So you can asynchronously index your data while your ingestion is going on. And the unique feature about Hudi is that these table services, apart from indexing, the compaction, cleaning of the data, the clustering of data to support efficient queries, they all keep running in the background while your ingestion is going on. So your readers and writers they don't have to worry about, whether my older data is getting cleaned or not, whether my data layout is optimized or not. They don't have to worry at all, right? So writers, the ingestion writer, just go ahead, pick the data from the source, dump the data, done. The reader, go ahead, depending on the type of query that you want to do, either merge the base files, give me the results, or give me the latest snapshot from the latest base file. Done. What happens in the background is totally automatically handled by Hudi, these clustering services, compaction services, and cleaning services. So it's not just a table format. It's not just a transactional layer. Hudi has kind of become a platform now, which supports both streaming and batch style pipelines. And it has a self-managing data plane, as I mentioned before. You don't have to worry about compaction and clustering. It's suitable for very large-scale data processing. There are companies running Hudi at exabyte scale, and it has very loose coupling, as in you could run these different services independent of the ingestion, so you don't have to worry about that. Learn more about how Hudi became a streaming data lake platform, I would recommend going to this blog, which is written by the author of creator of Hudi. It's a very interesting blog. So what's the Hudi stack looks like? So as I mentioned before, lake storage forms the base, right? And then you have open file formats like Parquet, Hfile, Avro, ORC. These are for your data files. And this is the Hudi stack on the transactional database kernel layer, which supports concurrency control mechanism, table services, indexes, lake cache, table format, and timeline server. We'll get into the details of each of these in a bit. But essentially, you build lakes on cheap, scalable cloud storage, elastic cloud storage, and then this transactional database kernel helps you take care of all the other things, which supports both efficient reads and writes. And Hudi is query engine agnostic, so you can plug in any query engine. We have our connectors for Presto and Trino on the way. So Lake storage is nothing but a Hadoop file system compatible. So if you're on AWS, you have S3 and S3A file system. But what does Hudi do uniquely here? So Hudi has its own wrapper file system, which is size aware. So that kind of helps in automatically tune the file sizes for Hudi. So that's very important. Automatic tuning, it's really hard to do. And I don't think many open source storage lake formats provide that. Hudi taps into the lower level APIs of HDFS in order to do that. The file formats, sure, you can write Parquet files and Avro files, right? But Hudi has its own file format in the sense that you have a base file. That's the first, in a way, in a sense that when this file was written, it created a base file, and then all the updates for merge on retable. This is for merge on retable. The log files, the updates go to the log files. And these data blocks, so Hudi maintains for each file slice, it maintains what data block was updated at what commit time. And even when you roll back data, not just update, when you roll back data, Hudi maintains a rollback block within the log file itself so that it's very efficient to merge. While reading the table, you know what to return, what to merge, what not to merge, right? So all these changes are included. The smallest unit is this data block. It's not the file, it's the data block. That's important to keep in mind. A lot of the times when we talk about these lake storage formats, we think in terms of files, right? Data files. But for Hudi, it taps into the lower level APIs, and that block is the smallest unit of data. Yeah, one of the biggest use cases for where this helps is pre-materializing for masking and data privacy. So if you want to create a table and then you want to hide the data, mask the data, right? You just that whole view can be pre-computed with Hudi. And it's just a matter of single config that you need to touch, and it won't affect your reads and writes as much. Now let's go into the transactional DB kernel. So it's a table format for sure. Yeah, it's a table format. Oh, but what about the table format? As I mentioned before, right? You have this timeline as the event log, a serialized order of events. Hudi additionally creates a metadata table. And this metadata table contains different kinds of indexes, such as files index, which tells you which file is located at what partition for a given record key. The column stats index, which stores min, max, null counts for different columns. Then there is also Bloom index that is stored in the metadata table, which helps when a new record comes in to tag the location for that new record, which file group it should go to. So this internal metadata table itself is a Hudi table. That's important. We don't use an external storage system. We are not storing this in a RocksDB database or somewhere in a relational database, right? The internal metadata table itself is a Hudi table. It's a Hudi merge on read table. We also support schema on read. So that helps with schema evolutions, including use cases for drops and renames. Then let's talk a little bit, dive a little bit into the indexes. So like relational database, like your MySQL, Postgres, Hudi supports pluggable indexes that are consistent with transactions. This is very important. They're consistent with transactions, right? So you have indexing going on while your writes are coming in, right? So whenever some, let's say, indexing was running and your updates are coming, the index updates also get logged into a log file. Remember, this index gets stored in the metadata table. And recall that I said metadata table itself is a merge on read table. So metadata table has this notion, it is aware about base files and log files. So the new updates through the ingestion, they get the index updates corresponding to those updates also get logged to the metadata log files. So it's non-blocking, asynchronous. It supports column stats and range indexes, as I mentioned before. You could use simple Bloom index, local versus global. This concept of local versus global is also very important. So local index, it's very efficient. What it does is provide uniqueness guarantees in a partition, right? It could be any number of file groups within a partition. The uniqueness is guaranteed. Global index, on the other hand, guarantees uniqueness across partitions. So sure, there are trade-offs involved here. Global index might incur higher cost than local index. But if your use case is that you want to maintain uniqueness across partitions, then go for global index. Hudi also supports an external pluggable index based on HBase. HBase has a very nice tree map kind of structure, which provides for efficient point lookups. And there is an ongoing work on record level indexing and DynamoDB based index, again, in the category of external indexes for Hudi, right? The benefit of indexing, let's talk a little bit about the benefit of indexing. So without index, let's say you have these different 25 MB chunks, those are updates, and these are 100 MB base files, right? So each file, without index, each file will be merged against all updates. So that means the merge cost will be 100, for this particular file group will be 100 plus 25 into 8 times, right? 100 plus 25 into 8 times, 100 plus 25 into 8 times, so and so forth. So totally 300 for each file group. Total merge cost is 1200 MB. While with index, let's say two of these updates were pertaining to records in file group 1, and then another two to file ID 2, another two for file ID 3, another two for file ID 4. Then with index lookups, each merge cost is just 150 MB, 100 MB, and 25 to 25 MB blocks pertaining to that particular file ID, right? So then overall merge cost is 150 per file group, and that's for 4 file groups is 600 MB. So you see how this merge cost is basically half of that without index. That's a very, very crucial benefit of indexing. Let's talk a little bit about, I mentioned before that the different table services, they run concurrently with ingestion. So how does Hudi handle concurrency control? First of all, Hudi did not need multi-writer support when it started, right? So despite this asynchronous clustering or compaction, Hudi was very well aware, and it treated the normal ingestion writers differently from these table services writer. Let's call these compaction clustering writers as table services writers. And let's call the regular ingestion writers as ingestion writer. So it supported multi-version concurrency control, a non-blocking form of concurrency control. And this satisfied most our needs, right? But Hudi also supports, later on, there was a need for optimistic concurrency control. So for table services, it still uses the multi-version concurrency control. But now let's say you have not just one ingestion writer, but you have multiple ingestion writers along with these table services running concurrently. It's hard to differentiate between these multiple ingestion writers, right? You can still differentiate between any ingestion writer and table service writer, but it's hard to differentiate between these ingestion writers. So Hudi supports locking-based optimistic concurrency control, but still runs multi-version concurrency control for these table service writers. Clustering is aware when compaction is happening. Compaction is aware when cleaning is happening without really taking a lock. An ongoing work towards concurrency control is to support multi-table transactions. So far, the scope of transaction has been limited to one table, right? Multi-writers, but one table. But we are working towards multi-table transactions, and we are also researching into how we can support fully lock-free transactions, even in multi-ingestion writer scenario, right? Let's talk about the table services. So as I mentioned before, we have these table services like compaction, cleaning, and clustering, continuously running table services in the background. It's just a matter of configuring them every few commits. You can configure them depending on the frequency of commits or depending on the size of the data. It depends on your use case, right? Yeah, while clustering, you can mention what to the sort columns to cluster by. You can also mention different methods of clustering. You want to do Z-order clustering or not. In a nutshell, these table services are what make Hudi like a self-managing database runtime. Table services know each other. They when compaction is each of the table services is categorized into two stages. One is the planning stage and one is the execution stage. So when compaction is doing its planning, it is aware that if there is any clustering running, then what I need to do, right? Similarly, for any permutation combination of these table services. So services can be run continuously, asynchronously, or even if you're not sure, you just want to try it out, you want to start out without really running this asynchronously, you can even run it in line. So let's look at compaction, right? MOR table is compacted by default. It needs to be compacted. And compaction periodically produces new base files, which are the latest snapshot of the table. Compaction helps in reducing the write amplification. It keeps the query performance in check. Those are the benefits of compaction, right? You have upserts and deletes coming through while your compactor can keep on merging base and log files in the background to produce new base files. Clustering. Well, why do we want to do clustering? So clustering is a very nice way to balance the trade-off between high throughput and query performance, right? While a writer needs to only dump the data, for query, we need to optimize that data layout so that query latency, queries are very efficient, right? So this is always the trade-off between data freshness and query performance. So what you can do with asynchronous clustering is that let the writer do its job at a very high throughput and let the clustering do its job to cluster the data by certain sort columns, depending on your access patterns, right? Sort keys depending on your access patterns. So AWS has a very nice blog on how to use clustering. Of course, it's on AWS, but it also has some performance numbers, how clustering helped them with Amazon reviews data set, right? Cleaning. I wish cheap storage, sure, elastic storage on cloud, but it's not free, right? We still need to reclaim space, otherwise it can keep growing without bound. So Hudi supports different cleaning policy, and you can do lazy as well as eager cleaning. So lazy cleaner, eager should be clear by its name itself. The lazy cleaner, what it will do is it will generate the plan. It will let the cleaner delete the files. Actual deletion of files happen after a certain point of time, right? Now, we talked about table services, concurrency control, and indexes. We haven't talked about lake cache and timeline server. We'll get to that. It's in our roadmap. It's still in beta. It's not generally available. Before that, let's talk about SQL programming APIs. So we have this record payload interface, which is a very simple interface. You specify a record key and partition path if your table is partitioned, or empty partition path if it's not partition. And it provides these APIs to merge the records. And also, you could use custom pluggable strategies. Would you already provide certain default strategies? You could configure that. But if you want to have your own strategy of merging the data, go ahead and implement this interface, and you have your own strategy. The way it works is that you pull the data from the source, you generate the keys, then you do this pre-combine, which is the merge logic I was talking about. And the pre-combine sorts the data into different buckets. And then you do the index lookup, which file group that should go to. And hence you optimize the layout and commit the data. So Hudi supports this record level merge APIs, right? And that is why Hudi has a constraint of defining your record key field. It's very much like the databases, which asks you to define primary key for efficient reads and writes, correct? And Hudi has different types of key generators, automatic key generators, timestamp based key generators, or custom key generators. If you want to support, Hudi supports composite keys as well, just like databases. You could define multiple keys as record key fields. Let's look at the reader side. On the reader side, we have an integration with, so you could do, Hudi already provides a mechanism to automatically sync the table to Hive, and that unlocks interactive query engines like Presto and Trino. On Presto, we already have a Hudi connector since version 0.275. On Trino, there is a patch available. Keen users are welcome to try it out, and it should be ready to land very soon. It's near landing. The main thing is, the key thing is that Hudi uses engine's native readers, right? You are reading a Parquet file, let's say. Most of the time you're doing that, right? Parquet or ORC file. Hudi does not do anything special there. It will rely on the engine's native readers, the Parquet reader, and those readers are already optimized for you. It will give you the results. I'll come to certain optimizations that we are doing in the connector itself, but high level, that's the gist. For merge on read table, where you need to run snapshot queries on MOR table, you need to merge the base file and the log files. That's when we employ our merged log record reader, right? So we use the native engine reader to read the base file, but then merge the data using our reader with that base file and show you the result. Let's talk a little bit about the topmost layer, the platform services. There is a very useful platform service called Delta Streamer. Most people run Spark structured streaming to ingest from Kafka or event streaming sources, right? You could just very well use Delta Streamer. It provides you a very robust incremental checkpointing ability. And you just need to set up certain configurations. It will deliver commit notifications. Similarly for Kafka, if you want to, if you're a user who likes to work with Kafka Connect, then Hudi supports Kafka Connect Sync. Hudi has pre-commit validators. Before committing, you can run data quality checks. Hudi also support other services like creating a snapshot, taking a backup, which we call save point in Hudi terms, restore to a particular save point, do export and import. You can import any other Parquet table as a Hudi table. All these table services are provided by Hudi out of box. So what's in the roadmap, right? Before talking about roadmap, a little bit about our development community. As I mentioned before, we have over 2,000 Slack members, over 300 contributors, over 20 committers. The way it works is that anyone can propose new RFC on our Apache discuss list, and you can raise a PR on GitHub, label it as RFC. It will be reviewed by the community. And we use Jira for issue tracking. We do monthly minor releases and quarterly major releases. Minor releases are mostly bug fixes, kind of patch release. Major releases will have big features. To engage with the community, we do a weekly community on-call, office hours kind of thing, where we help users to troubleshoot their issue. We also actively triage issues in GitHub. We also do a monthly community sync call, kind of state of the union update on Hudi for the past month. In our roadmap, so today, what's ongoing, right? We already have these engine integrations. Presto, as I mentioned before, we have the connector out already. Trino, it's on the way. Spark SQL, already we released this in version 0.9, if I'm not correct, if I'm not wrong. But we have also optimized it, brought it on par with data source rights. We are also working on non-keyed table. So far, the constraint has been that you need to specify a record key, but we are also trying to integrate with a primary key less data model. With the latest version, we brought a lot of usability improvements, enhancements. Then going forward, what we have is this transaction database layer, which we already have actually. A record level index is still in progress, but we have indexed columns, eager config detection. Oops. All right. And we have integration with Pulsar sources. Kinesis is in progress, and Snowflake external table is also in progress. If you go to GitHub PR list and filter by label RFC, you'll find RFC for these different sources, just for interested folks calling it out. Going forward, what we want to do in the transaction database layer, as I mentioned before, we want to do fully lock-free concurrency control for multi-writer scenario. We want to have more engine integrations, and that's where multimodal index will help us. So sure, we can do partition pruning, predicate pushdown even today with the native engine readers, but multimodal index can also further help with employing. Today, if you look at the Presto Hudi connector, it cannot make use of the column stats index beyond Parquet metadata, right? We want to use the indexes that are stored in Hudi's internal metadata table. So that's what we are working on. Now, on the platform service layer, we want to integrate with Airbyte and incremental ingest for Google Cloud Storage. Then there is a very interesting feature of error tables. Why fail the ingestion just if few records were not inserted or updated? Instead, what we do is, what we can do is go ahead with the ingestion. Don't fail it, don't block it, right? But those records which produced errors, log them into the error tables so that a customizable job created by the user can later, backfill, or you can use it for various purposes. And in 1.0, we want to provide, in the database layer, we want to provide time travel updates and deletes, multi-table transactions, as I mentioned before, support more and more index types based on Lucene and bitmaps. Then be on par with Hive for other query engines as well, Presto and Trino, and then work out some early integrations with Dask and Ray, while providing APIs in different languages. But for platform services, we have planned for a lake cache. Right now, Hudi does not have a caching. Well, it does sort of have a caching layer, but a fully functional kind of caching server, that's not there. And we plan to release this meta server, make it generally available. We already have a timeline server. So if you go back to our stack, you see this timeline server and lake cache. Timeline server today is available in Hudi. And it actually helps. You don't have to really load the timeline, incur that cost of file IO each and every time. If you enable this timeline server, today it's embedded with the driver itself, but we plan to decouple it. And Lake Cache, as I mentioned before, a separate caching server for the lake. So that's all in our roadmap. Keep an eye on our blog posts on Hudi website. I'll very briefly talk about the meta server, how this really helps data lakes. So meta server will be, as I mentioned before, embedded with the Spark driver itself. What it does, it's backed by RocksDB, but it's updated incrementally on each timeline action. So you do an update on the table, it will produce a commit on the timeline, event on the timeline, and your meta server gets updated. So it's very, very helpful in case of streaming use cases. You now have a server responding to you at any point of time, what was the update, and if you think of a caching layer on top of it, it does not really have to go through the storage, lake storage to fetch the file, and it avoids that file IO. Lake cache, that's again coming coming in future very soon. So in databases, we have this concept of buffer pools, right? Lake cache is very similar to that idea. So think of a least recently used cache, which stores your data, like what were the deltas for a particular file group. It stores that, and you don't have to really look at the commit metadata. You just get the result directly from the cache, which speeds up your query. As I mentioned before, to engage with our community, you can head over to join the Slack community, join our community syncs. I've specified the links here. Yeah, so, I really like to thank Microsoft and Data Platform Gigs for providing me an opportunity to talk about the Hudi project and its many benefits. I hope that many of you come and join our Hudi community syncs. Um, Help us with contributions. Any idea you may have, just shoot a devless thread, and the community is very engaging. Committers and PMCs will certainly help you through that. I also hope that you would provide some feedback, or any questions you may have. You can just go on Twitter and tag me and ask me any questions. I would be more than willing to answer that. Thanks for your time. That's all for now. Thank you.